our next topic here. So our zero force members. Now I've seen this asked explicitly in the exam as a point blank, here is a truss. How many zero force members are in the truss? Another way you may see it, although they don't explicitly come out and say, hey, use zero force members on this problem, you'll get a truss and they'll say, find members, forces in member 1, 2, or 1, 2, and 3. Now, at first glance, that doesn't have anything that mentions zero force members, but that's always where I would start. Why? Let's say the problem says we have 3 member forces defined in a truss. If I can eliminate 1 or possibly 2 of those to say, right off the bat, they're zero force members, well, I've just reduced my computation time by 1/3, if not 2/3. So I don't have to do method of joints, method of sections, method of joints. So it's all about time management, and that's how I would approach a problem that has multiple member forces in a truss. The first thing I'm looking for is a zero force member. All right, now let's jump back to the slide here. It says what? Zero force members, sure. Just mean for a given loading, some members do not take force. They are always, can I get a couple more always in there? Always needed for stability. Do not, and I've had this happen. Some folks will say, you know what, Dan? I looked at that truss. I took out 5 or 6 members and then went back to that M, R, and 2J. And you know what? That truss fell down. It's like, yeah, it probably would. You take out half the members. So zero force members is like a snapshot in time. They're saying where the load's applied currently, some members don't take force. The wind changes direction, whatever you want to call it. Force goes to a different location, totally different problem. Got to reanalyze the entire thing. So the important thing here, again, zero force members always needed for stability. Just so happens we're taking a snapshot where some loads are shown, and we're going to identify them. Now we're going to look at a couple rules, kind of 4 of them that can quickly identify zero force members. The idea here is to do what? You get a truss on the exam and it's got 20 joints. There's no way I am doing 20 free bodies using method of joints and spending 14 minutes on this problem. I'm going to go quickly through the truss with the 4 rules, and that's going to give me the zero force members I need. So let's see what they are. Rule 1 says only 2 members at the joint. Does that work for 3, 4, 5? Nope, 2 only. No external load being applied, then both of them go to 0. The dashed line in the figure is just to show a 90-degree angle to tell you that it doesn't matter the angle between them. 2 members of the joint, no force. They both go to 0. Easy peasy. Rule 2. 3 members at the joint, max. Does it work for 4, 5, 6? Nope, 3 only. 2 of which are collinear. In other words, in the same line of action or separated by 180 degrees. In this example, FB1 and FB3 are the collinear members. They take force. It's the odd man out. FB2, which goes to 0. Now the reason for that, if we drew the force triangle for FB2, it looks something like this. You say, well, what about the component parallel to the collinear members? Obviously, they're in equilibrium with that. I don't doubt that. I'll say yeah. But then I would counter that. What balances out the perpendicular, i.e. that guy there? There's nothing. Nothing balances that out. So it goes to 0. Because you've eliminated one of the legs, that's how the whole thing just falls apart. So that's the justification why FB2 goes to 0. Nothing balances the out-of-plane force.